So why do we want to do decadal prediction? So I'm showing this schematic here extracted from the last IPCC report, chapter 11, showing how until the last CMIP 5 exercise, we had prediction on short time scale, weather prediction, seasonal prediction up to few seasons, and the long-term climate projection on up to centuries or several centuries. And we really had a gap for this few years to a decade where we didn't have really reliable information to provide to any users, while there was really an increasing demand to give this projection for a number of applications that you can imagine, like water resources, agriculture, fisheries, insurance, and also because of the risk of abrupt changing happening really in the next few years. So the motivation really was, given the information we can get from the climate system, in particular from the ocean, can we extend the success of seasonal prediction to decadal timescales if we describe the initial state and the boundary condition? Because you know, those who are familiar with short-term prediction, that weather and seasonal prediction are what we call an initial value problem. You initialize your model and then you run your forecast, while the long-term projection, you really don't put initial condition, but just the information, what we call the external forcing. So it's a boundary problem, forced boundary problem. The decadal prediction lie between these time scales, so it's really what we call the mixed initial value and boundary problem. So what type of things we would like to predict? Just illustrating two examples here. One is a California drying. So you probably heard that California region, so in the United States, had experienced really dramatic droughts over the past few years. So between 2011 and 2015, it was the driest years ever recorded. And it's nicely illustrated here from this satellite measured by the NASA GRACE satellite that shows the loss in accumulated water. So here red, from green to red, it's actually the decline in water, in accumulated water storage. And this is one of the area where the US gets most of this water, so it's really important for management. And so between 2011 and 2014, there was a really big water loss. And of course, there are a big societal impact for that, in particular for agriculture. Even though there are some advantage, wine has been much better over these years, so there are some industries that find some advantage, but overall the state has suffered a lot from that. And if we look at some climate index that kind of represent this drought, called the Palmer Drought Severity Index, so it's kind of a precipitation index if you want. And if you look at like this blue time series and think of it as a precipitation, it's not just like a decline, like a trend that is forced over the past decades, but there is really some decadal variability in this time series, and suggesting that maybe it is related to some ocean changes, and indeed it is related to El Niño Southern Oscillation and to a longer timescale variability in the Pacific that we call the Pacific decadal variability. So there is some hope that maybe one day we could predict some of these changes with some information about the ocean. Another societal, very important example is hurricanes, tropical Atlantic hurricanes. So you heard that last week there was this terrible, although really impressive and magnificent cyclone that was in the tropical Atlantic over Haiti. So it was a Category 4 tropical hurricane, and that hit Haiti and unfortunately made over 800 deaths. People died from that hurricane in that area. And so it's clearly the kind of thing that we would love to be able to predict. And why do we think we could predict that? It's because if you look at the time series representing the frequency of these tropical cyclones, represented here by what we call this North Atlantic Power Dissipation Index. If you want, it's a type of accumulated energy that is expended by a tropical storm or a cyclone, shown here in blue for this tropical Atlantic. It shows also some decadal variability. It's not just like short-term variability, but some decadal variability. And interestingly, in blue, this is a sea surface temperature average over what we call the Atlantic Main Development Region. So it's this tropical Atlantic area where tropical cyclones arise. And it's, as you see, even with your eye, it's quite highly correlated. And so it happens that if we would know really well the information of the ocean in this tropical Atlantic, we could get some information maybe about these tropical cyclones. And what's interesting, if you look at this time series, is that there have been few decades where tropical cyclones have been quite inactive, and we entered then another era with the change point where we entered active years. So it's very interesting to try to understand and predict these changes. Okay, so now practically, where do we expect to find some predictability from the ocean? Not everywhere, because as Michel said before, there is a limit of predictability in the system. The system is chaotic, so we need really to look at the places where we know there is a chance to find something. And this is here represented by what we call a potential predictability. So you just see it as it's a variance, it's a fraction, it's a ratio of the variance at decadal timescale over total timescale. So if you want areas that are here red, orange or red, means that the variability on decadal timescale is larger than at any timescale. So it tells you that over these areas, you have a chance to have maybe some decadal predictability because there is some decadal variability. So that's the first step. And the regions that show up there, it's from a bunch of semi-3 model, but it's the same from recent model. It's really the North Atlantic, some of the North Pacific, and the Southern Ocean. It means this is where you want to look first. Okay, so why do we have these regions that show up? In the Atlantic, it's because of what we call the Atlantic multidecadal variability. It has attracted a lot of attention over the past decade because of the many climate impacts it's associated with. So what is this Atlantic multidecadal variability of AMO? It can be summarized by this pattern that's defined. The index is defined as the North Atlantic sea surface temperature averaged over this whole area. And then if you regress your sea surface temperature on this index, you get this global pattern. So it's characterized by these interhemispheric features. So when the ocean is warmer in the northern hemisphere, it's generally cooler in the southern hemisphere. And it shows this variability, some variance, larger variance around 40 to 60 years, but it's hard to say with the short record. And interestingly, it has been related to a number of impacts from Europe to the US in many areas of the globe: drought, rainfall, hurricane, dust, etc. So really, it would be, if this is a region where it's predictable and we're able to get some predictability of such a pattern, then we would be able maybe to give some information about the changes of these impacts that are really important. So why do we have this pattern that arise? A number of studies have been looking at what drives this variability in the Atlantic, and there is increasing evidence that the ocean plays a large role in getting this variability, in particular the ocean circulation associated with what we call the Atlantic meridional overturning circulation. So the sea surface temperature associated with this Atlantic meridional overturning circulation describes a change in heat transport. So when we have a larger an enhanced overturning circulation in the Atlantic, as described here by this stream function, we tend to have a warmer northern hemisphere. And when this circulation reverses, we tend to have a cooler northern hemisphere. And so one of the drivers of this Atlantic multidecadal variability would be these changes of variability, natural variability of this circulation. Which is good news because we believe that this is one of the maybe most predictable, in theory, at least in idealized model quantities. What about the Pacific? You remember that potential predictability global map showed some bulbs, red area in the North Pacific. So what drives the predictability in the Pacific? In the Pacific, it's much more complex. It has been recently reviewed, showing it's a number of phenomena. Anything that happens in the Pacific is related to El Niño to some way or another, even if it's at longer time scale. So there is a signature of El Niño on longer time scale, but more than that, what we call the Pacific decadal variability, so it's the counterpart of what I described for the Atlantic, but for the North Pacific, illustrated here by this pattern temperature and this decrease of the Aleutian law in terms of circulation, atmospheric circulation. And it's the mechanism that drive this Pacific decadal variability. It's a combination of ocean-only mechanism, ocean-coupled mechanism, and atmospheric forcing. So it's shifts in the boundary, in the western boundary current near the Kuroshio, and changes in the wind forcing and other phenomena. Which means that because if it's not one mode, it's an important message I want to say is this variability in different areas of the globe cannot be seen as a single mode of variability. They are usually really a superposition of a number of phenomena, and which means you cannot really see them. You need to represent all these phenomena correctly and predict all these phenomena correctly to get real prediction, which is very, very difficult to do practically. And it means also if among these processes, maybe only few will be predictable because only few will involve some ocean dynamics that will be predictable. And it's also something to keep in mind. So this PDO has been associated to snowpack, as I said, in North America, in particular US drought, and a number of changes in particular in ecosystems. So there are a lot of interest in trying to predict that. So what makes a decadal prediction system? So over last CMIP 5, it was the beginning of this coordinated exercise where a number of modeling groups have started doing decadal predictions. So what makes a prediction system? First, you need a global coupled model. You had a nice overview of what an ocean model and atmosphere model can be this morning and this afternoon. So you need a global coupled model. You need initial condition because you need to initialize your model. So for that, you need the best estimate of observed condition. And this is where reanalysis become important, and we need this reanalysis. So you need to initialize your ocean, you need to initialize your atmosphere, your coupled system in general. And so you do initialized runs, usually members, because you need this probabilistic approach to make an ensemble. So usually 10 members, and over the past, for the past exercise, it was every 5 years or every year between 1960 and up to the present. And these initialized runs are also forced by external forcing, radiative forcing, because as I said before, it's a mixed initial value and boundary value problem. So you also need the external forcing there. And in parallel to this initialized run, you need an uninitialized run with the same forcing as the initialized run, but no information about observation. And why you need that? Because you need to assess if you have skill, if it comes from the added value of initialization. Because if you get something, it's skillful, but then you could have got it without this initialization, then it's useful, but then you don't need probably that expensive framework to do it. So, because models are imperfect, and unfortunately, you need to bias correct your predictions. And so this is a schematic showing in black where observations are, and typically where models, free climatology, free running models are. And so if you initialize your model close to observation, you're going to be close to this black line. But very quickly, the model is going to go toward its own attractor. So if you run your model for 10 years, this forecast I run for 10 years, then you're going to get this type of behavior. So then if you want to analyze your model and assess its skill, you want to bias correct this. So what we do usually is we remove a lead-dependent climatology from these hindcasts. So everything that you find usually is bias corrected in this decadal prediction. So what it looks like for global mean temperature, just an example. The black line is global mean temperature observed, and the different red lines are what we call the historical simulation, so the typical forced run without initial conditions. And the red line is the ensemble mean of this historical run. And what decadal prediction give you is what is shown here in black. So you just start closer to the black line, and you get this 10-year prediction, and you have individual forecasts. So what it shows here is usually you want to compare with the historical run, and for global mean temperature, you're not going to be very different because the global mean temperature is mainly forced by external forcing, but it's for really regional features that you want to see what's the added value from initialization. I might skip that for now. So there are different type of initialization and systems. So I'm just here giving an example of the CNRM CERFACS decadal prediction system. So the coupled system we used that was used at CNRM CERFACS was Arpège, Climat, NEMO. You heard about these two models already today, and Gilato for the ice. There was a coupler and then a river routing. And the way we initialized this model was through what we call a nudging toward the NEMO-VAR ECMWF ocean reanalysis. And so so this was a technique adopted for this particular decadal prediction system. It's documented in this paper. And if you look at a number of groups that are participated to this decadal prediction activity, you will find a number of techniques as was presented for reanalysis as well. So I'm just listing here 4 just to illustrate that. For example, the METOFIS, the GFDL, the NCAR. So the METOFIS used an initialization called depresses. They used an anomaly assimilation, and that included observation, direct observation of temperature, salinity, a number of direct ocean data. The GFDL model also used this reanalysis, but in that case it was a coupled assimilation. And interestingly, there were other groups that did some decadal prediction without direct information from observation, but from what we call just an ocean force simulation. So saying we have information from the atmosphere, and we just run an ocean simulation forced by the atmosphere, and we're going to assume that we will get the basic information about the ocean just forced by the atmosphere, and run the prediction from this initial state. I just want to highlight that basically they are reconstruction of observations in these different initialization techniques that are very, very different from one group to another, and it's very difficult to say how that affects the skill. It's really difficult to say whether putting observation gives you higher skill or not on this time scale. So this is what it looks like. What are the results for surface air temperature? This is just from a bunch of the CEMIP5 model. This is a paper by Bellucci. The top row shows this is for surface air temperature, and this is a skill score. So red, high value of red tells you where there is skill. This is average over lead 2 to 5 years and 6 to 9 years. And the lower panel, this is a ratio of squared error, and this tells you if it's red, it means that there is an added value of initialization, basically. So this is the total skill, but it could be red because there is a forced signal from external forcing. And what you want to know, as I said initially, is do you have skill because you added these initial conditions, in particular from the ocean? And when it's red, it tells you, yes, here on 2 to 5 years, I got more skill because of initialization. On 6 to 9 years, I got it there. So it's quite disappointing if you look at this picture. For surface air temperature, there are not many areas that are red and significant, in particular at least 6 to 9. There are few in the North Atlantic where you expected it to happen, a little bit in the North Pacific, not much, but it's really small. And this is for surface air temperature. If we look at precipitation, it's even less, actually. So another important point is we want to know what happens over the ocean, but we also want to predict what happens over land. And there is really limited skill on this time scale over land. So again, it was a bit disappointing at first. But it showed that when you look at more integrated area, which makes sense, then you have less noisy system and you get larger skill. So this is another subset of CEMIP5, but showing similar results. And this is the surface air temperature average globally, and the dashed line is the uninitialized, so without initial condition, and the plain line is the initialized run, and that shows this is a correlation. This is a correlation, and this is the root mean square error, and this is the evolution with time. So if you just look at skill score, for example, for surface air temperature, the dashed line and the plain line are the same. This means that all the skill for global surface air temperature comes from external forcing. We shouldn't expect anything from initialization. If we look at this Atlantic multidecadal variability that I described earlier, here this plain line is above the dashed line, and quite significantly, it means that there is an added value from initializing the ocean. This is the good news. The Atlantic is more predictable. The Pacific decadal variability, it's not the case. There is no skill. And if we look at the Southern Ocean, there is no skill at all. So it's really the Atlantic that shows up as predictable at this decadal timescale in these CEMIP5 results. Another thing that appeared in this CEMIP5 exercise is you need to look at events that show a large signal, and in particular because the signal to noise is really small. And so you need to look at events where you had a strong signal, and to look at the mechanism that were associated to that. So a number of groups looked, including myself and different other groups, at what happened during the 90s. So the observation and different reanalysis, all reanalysis are able to reproduce that the North Atlantic subpolar gyre over the decade before 1995 was quite cold, anomalously cold, and then there is a shift toward a warming of the North Atlantic subpolar gyre, giving you the whole North Atlantic warmer by about 1 degree over the upper 700 meter than climatology. And so we try to understand what happened there and whether it was predictable. And a number of prediction systems were able to reproduce this shift, which is very important because it was associated with the change in the subpolar gyre strength and also with change in the ecosystem. So that happened to be quite predictable when the AMOC was well initialized in this prediction system, at least in these 3 prediction systems. And why? It's what happened during this 95 event is that in the 90s we had, this is the observed NAO index, in the 90s we have repeated positive NAO index for several years in a row, and the NAO index is associated with, when it is positive, is associated with fluxes such that it cools the Labrador Sea in the North Atlantic, and it enhances the deep water formation in the North Atlantic, which enhances the ocean circulation associated with this AMOC. And so what happens is that there is this lagged response to a positive NAO, which means when we initialize our model with at the right time before this 95 event, we are able to initialize the ocean state such as it is preconditioned and to give this increased heat transport a few years later. So the AMOC itself is not necessarily predictable, but if we initialize our system at the right time, then it's able with its memory to produce these shifts after a few more years. Other type of events that happen to be predictable is North Atlantic hurricane frequency, the same index that I presented earlier. We find that there is actually skill in predicting up to 5-year mean tropical cyclones in the Atlantic area in 2 systems, the Met Office and the GFDL model. But, and so this is when the model is not initialized, these are the prediction for these 2 systems, and these are observations, so it's quite bad. But the color line is when the model is initialized, and it follows better the black line for this hurricane frequency index. And what happened is actually we got a better representation of the Atlantic sea surface temperature in this main development region when we initialized our model, and this was the reason for the skill. But here I would be really careful into interpreting this result, because what we found is this skill was mainly due to the fact that there was this change point that I highlighted earlier in the time series, which means sometimes you can have skill, but you really want to know whether your past skill will translate into future skill. And it all depends on why you got skill. And here really we got skill because we were able to get to persist to get this change point, but not really predicted for the right reason. So we didn't get really the skill for the right reason, I would say. So I would say that today we still have limited predictability of hurricane frequency and decadal timescale, but it's a very controversial subject. So people in the room might disagree with me. So something we might predict in the future, so just here something quick about what we want to look for CMIP6. So the runs are not done yet, they're not ready, but something happening now that we want to look in the next maybe decadal prediction is the North Atlantic cooling, and I think you will hear more about this on Thursday, but the reanalysis, this is from the Hadley Center reanalysis, and this is sea surface temperature over the decade between 1990 and 2004, the anomaly of sea surface temperature, 700 meter, upper 100 meter temperature, and salinity over 700 meter. So before 2004 and after 2005, and that shows this North Atlantic eastern cooling, and that propagates at depth. And so this is a strong signal, and this is the type of signal we want to look in the decadal prediction system to see if we are able to predict it and for what reason. And the recent study that analyzed this cooling suggests that this cooling of the North Atlantic is happening at the same time as there is a decline in the density in the Labrador Sea. This is this red line here. This is the density at depth in the Labrador Sea, and it seems to have decreased over the past few years, and so suggesting that there is maybe a decline of the overturning circulation at the same time as we observe a warming at depth. So the warming that we saw during this 95 near the surface has propagated at depth in the ocean, and this is a delayed effect that we see now probably in the ocean that gives us this decrease in the circulation and maybe this cooling at the surface. So I would be really curious to see what we see in the future about that. So I'll just finish by highlighting some issues and challenges of decadal prediction. As I mentioned earlier, so we use coupled models for this. Models we use have really large biases in a number of areas of the globe. So the drift issue that I mentioned is illustrated here again for the CNRM CERFACS model, and you clearly see how the drift happened when we initialize the model with observation. And this is really an issue. Even when you bias correct, we are developing a number of techniques to bias correct the prediction, but it's still an issue because even if you bias correct the time series you're interested in, you don't necessarily bias correct everything. For example, you don't bias correct the teleconnection that are wrong because of your drift. So it's really challenging to get rid of the effect of bias correction, the effect of drift, and identify the effect of model biases on the prediction. Another issue that has been mentioned today, in particular by Simona, is that we are dealing with an observational system that is continuously evolving. This is wonderful because we get more and more observation, but it's very difficult when you build ocean reconstruction because they're not continuous. The data that they ingest, the quality of the data, the number of data, and the method is not continuous in time. And what you want is define a climatology. In order to look at this anomaly, you remove a climatology. So if your climatology is not constant in time, then you introduce a number of spurious effects that you see in the prediction. So this is really a challenge to work with this decadal prediction. And a last point that I want to highlight, and this is a figure that was shown earlier this afternoon by Andrea, it's that these initial conditions that we use for decadal prediction, it was true for the seasonal prediction as well, they are reconstruction from the present state, but they are not real observation. And so they have a number of issues. And so when we start looking at the different reanalysis, as was done in this paper by this intercomparison of reanalysis that were used for this decadal prediction, this is shown just for the AMOC at 26.5 north, you can see that even though these are all from reanalysis that were used for decadal prediction that ingest temperature and salinity. They ingest about the same data, but this is what they show in terms of the variability for the AMOC. And one of the reasons is we don't have observation at depth. We don't have observation below 2,000 meters. So as Simona said earlier, the models just do what they can and what they want to do. So there's a lot of uncertainty, I believe, comes from that. So it's really a challenge today to have good reconstruction to initialize the decadal prediction. So to conclude, at global scale, there is decadal predictability. At global scale, the decadal predictability arises mainly from external forcing, but there is some added value of initialization, not everywhere. Mainly in the North Atlantic, it's still quite poor in the North Pacific and Southern Ocean for a number of issues associated with the model and the initialization. There are still a lot of efforts to do in order to get larger scale over the land and for quantity that we're interested in, like precipitation. So we need more efforts on initialization methodology. We need more efforts to improve our models, to develop better drift correction, to understand the origin of the biases in the climate models and how these biases affect predictability. As I said, we need to reduce the uncertainty of initial condition. One way is to look at these different initial conditions and compare them. So I really appreciate the work of intercomparison between the reanalysis that has been done. And really, the most important point, I think we need to better understand the mechanisms that are associated with this decadal predictability, because you want to know if you have predictability, it's for what reason and is it for the good reason. So I would conclude by saying that decadal prediction are really at an infant stage, and even if it shows limited skill, it's very useful to improve the models, to improve our understanding, and they have been a good opportunity also to bring together community of climate modelers with a community of observation, and also to learn from all the efforts that has been done in the seasonal forecast community. Thank you for your attention.